No risk, no reward. That's a common saying that illustrates how risk and reward go hand in hand. This is certainly true in severe storm operations. Minimizing risk is an option, but one that greatly reduces the reward, that being the value that MIA and radar data combined can bring. This important module focuses on how to manage rather than just minimize risk in severe storm operations. From this module, you will learn about what distinguishes risk from uncertainty, differentiate between minimizing and managing risk, understand the sources of risk from each of the data sets used in severe storm operations, assess how to apply the weigh the evidence approach as a means of managing risk, and ultimately understand the role of MIA in augmenting, not replacing, other warning-related data sets. Hi, I'm Pete Wolf. With reward comes risk. You can't invest $1,000 in the stock market and expect to earn $10,000 in a few years, right? You have to invest more, perhaps $5,000 or $7,000 to achieve that result, and thus you're risking greater loss. Likewise, radar data offers us limited skill in the warning program. Incorporating near-storm environment data can help improve results, but there are risks that can lead to bad decisions, such as using bad data, or having an inaccurate interpretation of the data, or wrong conceptual models, even issues like stress and fatigue. In my view, it is the risk associated with MIA, and radar operations for that matter, that make it unwise to combine these tasks with others in operations. Distractions and fatigue can lead to mistakes. You see, utilizing MIA in severe weather operations is kind of a double-edged sword. Doing so correctly can lead to improved results, but doing it incorrectly can lead to worse results. Early in my SIU career, back in the early 2000s, I ran a short WES exercise with a forecast office staff involving a supercell that became tornadic. For half of the staff, I provided accurate near-storm environment data that clearly showed tornado potential, strong low-level shear, low LCL heights, and so forth. For the other half, I provided realistic but inaccurate environment data that showed a favorable combination of instability and deep layer shear for supercells, but had weak low-level shear, high LCL heights, and so forth that suggested tornadogenesis was unfavorable. I then sat behind each forecaster and watched them go through the radar data and make warning decisions. No surprises from the half of the staff with accurate environment data. They quickly recognized the mesocyclone and issued the tornado warning with an average of 20 minutes lead time ahead of the tornado. For the other half of the staff with the inaccurate environment data, they also recognized the developing mesocyclone and issued severe thunderstorm warnings for the large hail, but they did not issue tornado warnings, at least not until after the tornado formed. As I sat behind them, watching them recognize rotation and then move on to the next radar scan, I'm pretty sure my facial expression looked something like this. Now, I'm confident that without the bad environment data, they likely would have issued tornado warnings, albeit with much shorter lead times, as we commonly see in real-time events. Likewise, radar data provides risk too, due to potential error. Just as accurate radar data can lead to good warning decisions, inaccurate data or inaccurate interpretation can lead to bad ones. The thing about risk is that fear feeds on it, and that's not a good thing. Fear leads people to trust their instincts rather than trusting the data or the science. The storm is starting to look bad, I better get a warning on it. Fear prevents good IDSS communication. Should I communicate that if I'm not sure if it's going to occur? So as a result, we try to minimize risk rather than manage risk. This is all discussed in the module. Let's focus on understanding what is meant by risk, how it differs from uncertainty, and what we're referring to by the phrase risk management. So what is the difference between risk and uncertainty? Well, uncertainty relates to the probability of the occurrence of an event. Risk adds consequence to that. So risk is the probability of that event occurring and the significance of the consequence of the occurrence. So, to understand when a given decision is risky, one must have an understanding of potential impacts resulting from the occurrence or non-occurrence of the event. So in essence, decisions are riskier over population centers than out in unpopulated territory because the consequences of a wrong decision are greater over population centers. So risk is defined as a chance of something happening that will have an impact on objectives. It is measured in terms of likelihood and consequence. Risk management, therefore, is defined as the systematic application of policies, practices, and procedures to the task of identifying, analyzing, assessing, treating, and monitoring risk. Do you consider risk when it comes to convective warning decision making? Here are some interesting questions. How risky do you think it is to incorporate mesoscale environment analysis data or utilizing radar in severe weather operations? Based on the definition of risk, it would have to depend on the situation, as the level of uncertainty and the level of risk changes from one situation to another. Therefore, the correct answer for both questions would be it depends. Can you think of some issues that can hinder success by creating risk? Consider, for example, that the data sets we use are not always complete. The data are not always accurate. Our interpretation may not always be accurate. And we may also be distracted, fatigued, or stressed, all of which can impact data interpretation. There's always a risk to some level of things going wrong. Let's try a simple exercise here. I have a 12-letter word below. Each dash is a letter. I'm going to reveal a few letters at a time and see when you can come up with the correct word. So here we go. Can you figure out what the word is at this point? How about now? You're probably getting a good sense of what it is. In fact, the word is verification. It's a simple exercise to demonstrate that the more clues you're given, the more likely you're to come up with the correct answer. Now try this exercise, and this is the only clue you're going to get. What is this word? You're probably thinking warning, and unfortunately you would be incorrect because the correct answer is watching. Now, how is that possible? The third letter was supposed to be an R, and it's only a 7-letter word. Well, welcome to the world of mesoscale analysis. If this exercise irritates you, then you know how it feels when the data sometimes lets you down. Consider an example where the environment shows that conditions are unfavorable for a tornado for a given storm, yet you get a spotter report of a tornado leading to a tornado warning issuance. That can lead to frustration. So how can the data we use fail us and thus create potential for bad interpretation leading to bad decisions? Consider satellite, which can be a powerful tool for looking at near-storm environment information, except when your view is hindered by widespread high cloudiness, like in this example over Arkansas and Mississippi. What about radar data? It can be helpful for showing signatures and boundaries, things that can influence hazards, but they're harder to see if what you're looking for is a long way from the radar site and you're looking 8,000 or 10,000 feet above the ground. You may not see those key features. Model data also can be problematic. When the data are accurate, they're fine, but oftentimes the data are not accurate. They contain a level of error. Model soundings, like you see in this example, are often smooth versions of reality, and those that may smooth out important features that can make a difference on interpretation. Even spotter information can be problematic sometimes. The reports can conflict with the above information, or they can conflict with each other based on the location a spotter is in. Here's a short exercise from a 2003 presentation. We're going to focus on 3 primary data sets used in warning operations: radar, spotters, and environment. We're going to focus on the southern supercell shown here. I'm showing you a 0.5 degree reflectivity and SRM image. Based only on the radar data, what type of warning might you issue here? The radar does show rotation on the lowest slice there. There is some potentially questionable data in there, but in general it does show rotation on the southern flank of the storm, so you might go with a tornado warning with no other data to go on. Now what if we had high-res model soundings that showed a strong frontal inversion at and below 775 millibars because of a surface front that's located 50 miles to the south of the southern storm? Above this inversion there is moderate instability and strong speed shear to support supercells, but the environment data suggests the storms are likely elevated above the inversion. With this information, you might then go with a severe thunderstorm warning. Based on rotation, you might throw in a tornado tag, but you might go severe at this point. Now, what if that data was old and the latest model soundings show that the surface front has reformed just south of the southern storm, with a much weaker and shallow inversion shown on high-res model soundings. We're now seeing 0 to 3 kilometer CAPE up to 100 joules per kilogram. That might change your mind back to a tornado warning with this new information. What if in the county the storm is about to exit, law enforcement received a few calls about funnel cloud sightings with the southern storm? Again, that might lead you more towards the tornado warning decision. Now, what if the southern storm is tracking across unpopulated territory? In the new county, the AWIPS cities map shows no towns in its track across the northern portion. Well, for a marginally severe storm, that might lead you to hold back on a warning, but for one that has a potential for a tornado, it might not change your mind. What if you had a spotter at point X, east of the storm, looking to the west, reporting a lot of scary-looking scud clouds, but no funnel clouds or wall cloud? The spotter cannot find any distinct cloud lowering or rotation. I'm not sure how much credibility you would give this report, given that the forward-flowing downdraft precipitation is likely in the spotter's way, so you might continue with a tornado warning decision. If later you get a spotter at point Y looking due north, seeing a well-defined rotating wall cloud with a funnel cloud extending halfway to the ground, it's also heading towards town A, which is not on the city's map in AWIPS. All of this points to a much higher probability of a tornado and thus a tornado warning decision. So what happened? In this case, the southern storm produced large hail as well as a large tornado. This wasn't a real case. It actually is set up in this exercise to mimic another case that was an actual event that occurred in much the same fashion. It occurred in mid-2001 in southern Kansas. In that case, an EF4 tornado struck the town of Hoisington, Kansas, a town of 2,000 people. In that actual event, a severe thunderstorm watch was in effect. We had a surface warm front initially over northern Oklahoma with a near-surface inversion yielding elevated supercells with very large hail, and severe thunderstorm warnings were out for that. But during the 2-hour period prior to this tornado, the low-level jet rapidly intensified over southern Kansas, with the warm front reforming just south of Hoisington. Wind profilers showed a bullseye of high SRAs just along and north of the boundary. The low-level inversion weakened as dew points rose, supporting near-surface-based supercells with strong mesocyclones. In addition, the town of Hoisington was not on the AWIPS cities map at the time. So severe thunderstorm warnings were issued for very large hail, but no tornado warning was issued for the storm. This was an example of mesoanalysis failure, where the rapid change in near-storm environment was not noted until it was too late. Here's an interesting quote from the captain of the Titanic. It relates very well to the issue of not expecting anything bad to happen because nothing bad has happened to you before. As is quoted here from the captain, "In all my experience, I have never been in an accident of any sort worth speaking about. I have seen but one vessel in distress in all my years at sea. I never saw a wreck and have never been wrecked, nor was I ever in any predicament that threatened to end in disaster of any sort." And of course, 6 years later, we all know what happened. So risk was enhanced by not knowing the potential consequences that could occur. So why is risk management important in convective warning decision making? Because there's a level of uncertainty that exists with the data that we use, be it radar or environment or spotter information. Are the data accurate, and is our interpretation of the data accurate? There's considerable uncertainty that exists with our knowledge of environment processes like tornadogenesis. It's still in the realm of theory. There's still vortex studies being done on trying to better understand tornadogenesis in different scenarios. The potential consequences also vary for storms threatening population centers versus those out in the middle of nowhere. What factors could increase the risk of an incorrect warning decision? Consider this storm, and you're seeing the velocity signature for a storm about 70 miles to the west or west-northwest of a radar site. So what factors could cause one to make the wrong warning decision for this storm? Consider inaccurate data, such as what you're seeing on radar imagery. Is that really representative of what's going on, or is there error? Incomplete data, such as lack of surface observation coverage or no spotters to help interpret what the radar is showing. Inaccurate data interpretation, inaccurate conceptual models or other knowledge, such as knowledge of population locations, tornado genesis in low shear environments if that's the case, and so forth. office distractions, such as a radar outage, even personal issues, such as having too many storms to deal with and thus fatigue, can affect results. So can you list several issues that affect the potential accuracy of the following data sets? Starting with radar. What kind of issues potentially can exist with radar data that can affect the accuracy of your interpretation? Consider the beam width or height versus range. Your interpretation may be affected for storms much further away from the radar than storms close to the radar. The viewing angle, such as when dealing with radar velocity data and interpreting wind potential for a storm. Improper de-aliasing, dealing with higher versus lower resolution data. Having data overload in big events, if you have multiple sales cuts just trying to keep up. Dealing with range folding, and so forth. How about for near storm environment data sets? You may have to deal with inaccurate observations or a large gap between observations. Model data that's not supported by observations. Model solutions that conflict, or a single model having run-to-run inconsistency, and that type of thing. High resolution versus low resolution model output. How about spotter reports? They can have issues as well. You might have a lack of spotters to begin with. You may have spotters in different locations giving you conflicting reports. You might have numerous storms and you don't know which storm the spotter is reporting on, or the report itself might be inaccurate. So there are many issues that can affect the accuracy of the data you're looking at. As such, risk levels can vary with each event, with each storm, with each decision you have to make. For radar data, risk increases with increasing range from the radar or decreasing feature size. For environment data sets, risk can increase with increasing dependency on model data versus observational data, having varying model solutions, and decreasing observation coverage. Even for spotter reports, risk can increase with a decreased number of spotters available, a decreased level of training for the spotters who are reporting, or unfavorable spotter locations. There are other issues to deal with. Is the storm threatening a major city, or is it over the middle of nowhere? Given the existence of risk for every tornado threat, that is, uncertainty that a tornado will occur and the potential consequence if a tornado does occur, should we just issue a tornado warning for every rotating storm or every funnel cloud report? That's not really managing risk, that's minimizing risk. And sure, such action would greatly reduce the potential for significant misses, but at what cost? This is like having banks deny all loan applications to minimize the risk of defaults. How is this beneficial to the people? Here's an interesting question. Do you drive home after work each day, or do you just sleep at the office? It's much riskier to drive home after work, given the potential of meeting up with a drunk driver or driving in bad weather that could lead to accidents. It's much safer just to sleep at the office, but is that really what you want to do? Let's turn now to the weigh the evidence approach as a risk management option. The image here is from WDTD. So in this approach, the evidence, if you will, includes our knowledge of the data available for analysis, the knowledge of data not available, our knowledge of the accuracy and reliability of the data we have, and other factors such as storm history, potential impacts, and so forth. The image, I believe, has been updated in more recent times to something like this, the sum of all inputs. And here we desire inputs that give us a decision beyond a reasonable doubt, that is, a high level of confidence with regard to a warning decision. But a majority of the time we're dealing with a preponderance of the evidence, which way the evidence leads us to give us enough of confidence in a particular warning decision. So in the weigh the evidence approach, we focus on our key data sets. That's the radar, near storm environment, and spotter information. Each data set we have available provides clues, but also provides a level of error. The forecaster must weigh what the data indicate with the potential data shortcomings. So here's where we incorporate risk management into this. We incorporate our knowledge of risk, that is a potential for error, potential consequences, into the decision. And that needs to be done in the information that mesoanalysts provide to their team. So in this approach, for radar data, we would give greater weight to it for closer storms, larger signatures, better VCPs that provide us more detailed information. For spotter information, we would give greater weight to reliable sources, corroborating reports, and favorable spotter locations. For near storm environment data, we would give greater weight to model data supported by observations, reliable observations, corroborating observations, even multi-model agreement. So the most desired outcome is when everything is accurate and pointing to the same conclusion. That's when mesoanalysis in operations is easy. The problem are situations when the clues conflict on the potential solution, and when you have some data that may be inaccurate or incomplete. Then it's much more challenging. Recall the prior exercise of the presentation illustrated to the right that demonstrated this. So the mesoanalyst task also includes a QC step in data analysis, trying to assess the accuracy of the data you're utilizing. Here's a fascinating example. This is a time lapse, likely faster than what the eye would normally see, but nevertheless pretty fun to watch. And it reminds me of a case that I worked in Oklahoma many years ago. A fascinating monster supercell. It had 100 knot rotational velocity. That's 100 knots inbound, fairly close to 100 knots outbound. It was in a favorable environment for a strong, deep mesocyclone. The problem was that the conditions at low levels were not so favorable for a tornado, particularly very high LCL height. I also had a well-positioned trained spotter looking up at the storm with a clear view, saying that not only was no tornado, but there was not even a wall cloud. It was just a storm spinning like a top. And the storm was also over no population. So from the way the evidence approached, it led me to issue a severe thunderstorm warning for very large hail. Indeed, that's all the storm produced. There was no tornado from the storm. Nevertheless, I left the office scratching my head in disbelief that I actually did not issue a tornado warning with rotations that strong. So risk management in mesoscale environment analysis involves utilizing the data you have in an intelligent manner. So do you just go with the radar signatures you see, or do you try to understand what is going on, what radar biases or issues may exist? Do you just look at CAPE and SRH, or do you try to understand what those values really represent through sounding and hodograph analysis, and how accurate that data may be by incorporating the latest surface observations, especially if you're using model sounding and hodograph plots? Do you incorporate potential impact, such as the much greater threat for hazards crossing a city versus a swamp or a desert? In risk management, it's important to recognize what you know and what you don't know. So, in summary, unlike uncertainty, risk also incorporates potential consequences. That's why risk over a city is much greater than that over unpopulated territory. For the reward that mesoanalysis can provide in operations, there is risk to be assumed. Accurate and timely mesoanalysis in operations certainly can help, but poor application can hurt. Risk management is critical in all aspects of high-impact operations, including that for severe convection. The best risk management approach may be the weigh the evidence option. It's important to understand what you know and what you don't know, and to incorporate your interpretation of risk. It's important for the mesoanalyst to include knowledge of risk in the information provided to the warning and IDSS team members. Considerable reward can be achieved with MEA in combination with radar interpretation in severe storm operations, but not without risk to accompany it. That's a reality. There are potential issues that could lead to bad decisions, such as using inaccurate data or having an inaccurate interpretation of the data or wrong conceptual models, or even issues like stress or fatigue. Now, we don't want to necessarily minimize risk, as that also minimizes the potential gains that could be achieved. In the warning decision-making process, the weigh the evidence approach can help manage risk by incorporating our knowledge of what data we have, what data we don't have available, the issues that may be associated with the data that we're using, and also knowledge of the potential consequences as a result of hazard impact. As the mesoanalyst, it's important to incorporate a correct risk management approach to the information you provide your team. The next slide starts a short learning assessment with 7 questions. Each question slide is followed by an answer slide regarding that question. As needed, pause the video to answer the questions, write the answers down if you need to, then move on to the next slide for the answer. Good luck.